Have you ever really stopped to think about the fire that powers our world? I mean, everything from massive industrial boilers to the engine in a truck. Our entire society is built on combustion. But here's the thing. Getting the most energy out of every single drop of fuel? That's a hidden, super high-stakes science. So let's go ahead and pull back the curtain and really dig into the quest for the perfect burn.
And when I say high stakes, I'm not kidding. This quote from our source material, it just says it all, doesn't it? One single drop of oil, leaking every second, costs you over 4,000 liters a year. Wow. It just goes to show you, efficiency isn't some buzzword. It's about squeezing every last bit of potential out of our fuel.
So that's what this is all about. We're going on a journey to figure out exactly that. How do we get the most bang for our buck from every drop of oil, every lump of coal, and every puff of gas? It's a fascinating game of precision, chemistry, and some really clever engineering.
All right, so to kick things off, we got to meet the main players. Fuels basically come in three flavors. You've got your solids, right? Things like coal. They're packed with energy, but man, they can be messy to handle. Then you have liquids, like diesel, which are way easier to move around but need to be stored carefully. And finally, you have gases. Natural gas, for instance. Super clean, but they need some serious infrastructure, like pipelines or pressurized tanks. Each one comes with its own unique playbook of challenges.
Yeah, because if you really want to master combustion, you have to get to know the unique characteristics, you could almost call it the personality of the fuel you're using. These properties, they dictate absolutely everything, from how you store it to how it's going to burn.
So first on the list is viscosity, and really all that means is how thick the fuel is. The honey versus water analogy is perfect. Now, if your fuel is too viscous, too much like that cold honey, you've got a big problem. It's not just a pain to pump through pipes, it just won't break up into that fine mist you need for a really good, clean burn.
Okay, next up is the flash point, and this one is absolutely critical for safety. It's the absolute lowest temperature where a fuel gives off enough vapor that it could ignite with just a little spark. So for this furnace oil, that's 66 degrees Celsius. For engineers, knowing this number is totally non-negotiable. It tells them exactly how to store and handle the fuel to make sure things don't go, well, boom.
And now we get to the good stuff, the prize we're all after, the calorific value. You can just think of it as the fuel's calorie count. It's how much energy is packed inside. Now, when we're comparing different fuels, we usually look at something called the net calorific value, or NCV, and that's just the most practical, real-world measure of how much useful heat you can actually get out of it.
So let's see how this all plays out in the real world. Take a look at this comparison between a heavy furnace oil and a lighter diesel oil. Now, at first glance, you might think, hey, their energy content, that GCV, is pretty much the same. But the real story is hidden in the impurities. Just look at the sulfur and ash content in that furnace oil. It's way higher. And that stuff isn't just useless filler. It actively damages equipment, causing corrosion and all sorts of nasty buildup.
Now, let's switch gears to solid fuels, like this chunk of typical Indian coal. The breakdown is a little different here. You've got fixed carbon. That's your main heat-producing workhorse. Then there's volatile matter, which helps the coal catch fire easily. Moisture, well, that's just water you have to waste energy boiling off. And then there's ash. Oh boy, ash. That's the big problem because it doesn't burn. At all.
And this is where you really see the kind of trade-offs you're dealing with when you use solid fuels. Like, okay, having a lot of that volatile matter is great because the coal ignites super easily. The downside? You need a much bigger furnace to handle all those gases. And then there's high ash content, which is just a total liability. It doesn't burn, it can actually smother the fire, and it can even melt into this nasty glassy slag called clinker that gums up the works. Oh, and you have to pay someone to haul it away when you're done.
Okay, so we've gotten to know our fuels, now it's time for the main event, the combustion process itself. And believe it or not, there's a surprisingly simple, almost elegant, recipe for getting it right every single time.
And it all boils down to what engineers call the 3 T's of combustion. It's that simple. First, you need temperature. It has to be hot enough to ignite the fuel and keep that fire roaring. Second, you need turbulence. This is about creating a violent, chaotic mix of fuel and oxygen. And third, you need time. You just have to give the reaction enough time to completely finish. If you can nail those 3 things, you've pretty much unlocked the secret to the perfect burn.
And the difference between getting it right and getting it wrong is, well, it's night and day. When you get it right, that's called complete combustion. You turn carbon into harmless carbon dioxide and you release the maximum possible energy. But when you get it wrong, incomplete combustion, you get nasty stuff like carbon monoxide and smoke. And that smoke, that's literally unburned fuel. You're just watching your money and energy go right up the chimney.
And if you want to know the cost of that mistake in hard numbers, here it is. For every single kilogram of carbon that turns into carbon monoxide instead of carbon dioxide, you are throwing away 5,654 kilocalories of heat. That is just a staggering penalty for not getting the burn right.
All right, so knowing the recipe is one thing, but how do you actually control the fire in a real, live industrial boiler? Well, that's where technology steps in to tame the flame and make sure those 3 T's are happening just right.
See, in a perfect laboratory setting, you could mix the exact right amount of fuel with the exact right amount of air. But the real world is messy. The mixing is never perfect. So to make sure every single fuel molecule finds an oxygen molecule to dance with, engineers have to add a little bit extra. We call it excess air. It's just a practical fix for an imperfect situation. But, and this is a huge but, it's a really delicate balancing act. If you don't add enough air, you get that smoky, wasteful burn we talked about. But if you add too much air, you create a whole new problem. You end up wasting tons of energy just heating up all that extra air, which then carries your precious heat right up the stack. So the goal is to find that perfect sweet spot right in the middle.
So, what about that T for turbulence, especially with liquid fuels? How do we do that? The magic word is atomization. A modern burner basically works like a really high-tech perfume sprayer. It takes that liquid fuel and shatters it into millions of teeny tiny droplets. Why? Because that massively increases the surface area, which lets the oxygen get in there and mix perfectly for a super-fast, complete burn.
And you know, our ability to control this whole process has come a long, long way. The earliest systems were just, well, on or off, like a light switch. Then we got a little smarter with high-low controls, which gave us a bit more flexibility. But today, the best systems are what we call modulating. They are constantly, precisely adjusting the fuel and air mixture across the entire range, always hunting for that perfect, efficient burn. That's how modern systems squeeze every last drop of energy out of the fuel.
And that brings us right back to where we started. We've looked at the different personalities of fuels, we've learned the simple recipe of the 3 T's, and we've seen the tech we use to control fire. So in a world that's so focused on finding cleaner energy and brand new technologies, it really makes you think, doesn't it? Is it possible that one of the most important things we can do is just get better at mastering the oldest trick in the book, the perfect burn?